Good morning. This is Jonathan Weaver, professor in mechanical engineering at the University of Detroit Mercy. We're getting this lecture remotely since Dr. Kleinke and I are both attending the Conference on Collegiate Innovation in Washington, D.C. today. We're here to give you an overview of systematic innovation tools as we teach them at the University of Detroit Mercy and as we have applied in workshops in industry. The talk will be broken into three pieces. I'm going to give you part one on systematic innovation ideation tools. Dr. Kleinke, via video, is going to give you part two about innovation culture, process, and strategy. And then we're going to allow some time at the end for Dwayne Spiteman and Mike Kane, our colleagues who work at Innovation in Action together, to answer any questions you might have about how we apply these tools and techniques with practicing engineers. So part one, systematic innovation ideation tools. I'd like to begin with just our definition of innovation. If you Google innovation, you'll find millions of hits. Many of those are definitions. Most of them say something different. So we like to characterize innovation as invention plus commercialization, where invention by the U.S. Patent and Trademark Office definition involves something that is novel, useful, and non-obvious. If you couple that invention then with commercialization, we'll call that innovation. It's interesting that Wikipedia gives its own definition, and Wikipedia by many people could be considered innovative in and of itself, eliminating competition from the likes of World Book and Encyclopedia Britannica, etc. So we believe that an innovator is really part inventor and part entrepreneur, particularly that commercialization piece. The business proposition, commercialization side of things goes beyond invention. The systematic innovation techniques that we cover are highlighted on this slide. Some of these actually relate more to culture and process and strategy, so Darryl will cover those in the second half. But I'm going to give you a very quick overview of many of these tools and techniques. We came about teaching these tools after reflecting on the way we teach our design classes, capstone design, and other classes, is that we felt we were very weak on the concept generation piece, and even if you back it up a few steps, the problem definition and opportunity recognition piece. We felt like we were generally pretty weak there. If you needed to size a shaft for the senior design project so it wouldn't break, we were all over that. If you needed to do a finite element model, no problem, we got that covered. You need to size a heat exchanger, no problem. But why do you have a heat exchanger or a shaft in the first place? We weren't as good at justifying why our designs were what they were conceptually and architecturally. So this has led us over a number of years to start to look at tools that engineers can apply during the opportunity recognition and problem definition phase through the concept development phase to gain better confidence that you're putting a great concept on the table, worth doing a lot of engineering analysis and development on subsequently. One of the simplest tools we use, we refer to as bisociation, after Arthur Kistler's term in his book, The Act of Creation. It's this idea that two seemingly random thoughts can synthesize themselves in your mind to generate an innovative idea. The example shown, a pack of cigarettes with several slid out to various lengths on the left, and a picture on the right of the formerly Sears Tower, now Willis Tower in Chicago. The story goes that the architects working to get their bids accepted to build that tower, one of them got off the bus and had their cigarettes slide out to various lengths and immediately came up with the architecture kind of resembling that of the towers extending to different lengths. So we can teach this tool very easily. You can simply give somebody a random item like a toaster, ask them to list traits, characteristics, things they think about, how they use a toaster, etc. And then work backwards from there to try to draw connections to whatever it is they're working on. And in 5 minutes, you can teach somebody a tool beyond let's brainstorm and pray for a good idea. So that's one of the first tools and one of the simplest tools we like to teach. One of our favorite tools is biomimicry, the idea of design inspired by nature. The example shown relates to the early development of the Shinkansen, or bullet train, in Japan. When they first started pushing the speeds faster and faster through conventional existing tunnels, they had some problems with shock waves. As you build up a slug of air in front of the train pushing through the tunnel, and you hit the other side and you get a change in the boundary condition, you get almost a sonic boom. It's subsonic, but you get the shock wave effect. And not knowing how to handle this, they looked to nature for, in this case, a bird that goes through air and then into water very smoothly and cleanly without a lot of turbulence and chaos, and back eddies and the like. And they found the kingfisher. So they proceeded to redesign the front of the train after the kingfisher's beak, and suddenly the problem was gone. Similarly, they looked to owls to eliminate the wind noise from the pantographs running through the air at high speed. And by simply modeling the back end of the pantographs after the back edge of an owl's wing, they also got rid of the wind noise problem they had there. So nature's been evolving design for approximately 3.8 billion years on Earth. Mankind's only been around maybe 100 to 200,000 years, depending on when you think our species started to exist. And certainly civilized, high-tech industry hasn't been around for but a couple hundred years. And so we believe we can learn a lot by looking to how nature maps form and function and providing that as a specific tool for engineers. And there are ways to direct engineers to relevant functional solutions in nature, depending on the problem they're working on. Pain storming is an early opportunity recognition technique. The idea is to simply have students go out and observe pains, frustrations, jury-rigged products, etc., out in everyday life. If you find such a pain, then you have a problem worth working on. If you can solve that problem, somebody will probably be willing to part with some money to alleviate the said pain. The example shown was Bosch selling 7 1/4-inch circular saws. Top one has a cord, which tends to get cut off accidentally from time to time. And replacing it is somewhat expensive, going to buy the Bosch part, and time-consuming and difficult, even with small parts inside the handle that tend to fly apart when you open up the handle. So they simply redesigned it to receive the end of a standard UL, outdoor extension cord, cam lock it on so it doesn't continuously fall out. But now if you saw it off, the worst case is you get a different extension cord and you get right back to work. So we encourage our students to look for these pains and be observant of opportunities for engineering to address pain in the marketplace. Functional decomposition is another thing we encourage our students to try. Engineers really do map function to form for a living, but many people think immediately in the form domain and skip, or at least subconsciously, make the functional decomposition, but maybe never give it much thought. And so we like to encourage them to, in a very solution-neutral way, map the function of their problem to make sure they're considering a variety of ways to achieve all the key functions. So an example here is shown for the decomposition of a typical nail gun, such as a pneumatic one. And you notice in the bottom left it says trip of tool as opposed to trigger tool. Later it does say trigger tool, but out at the most general level where it says trip of tool, not using the word trigger opens up your mind to other ways that you might signal the nail gun to fire a nail. For example, it might notice the correct spot on a shingle where a nail goes as you drag it along and automatically fire a nail without me pulling a so-called trigger. So anyway, this is a tool that we like to apply. It's actually key to several of the other techniques that we're going to look at later, is to have a functional understanding of your problem. Axiomatic design is just one example there where you have to have that functional understanding of your problem. Axiomatic design comes out of the work of Nam Su at MIT, and he writes a book on his technique, The Principles of Design. But it comes down to 2 principal axioms. Is that axiom 1, you want your functions to map independently to your design parameters. And the second one he calls the information axiom. and that simply says the simplest design that satisfies the independence axiom is likely your best design. Simple way to understand what he's saying is to consider the typical lavatory faucet on the left, where as a user you'd like to control both flow rate and temperature. But the design parameters you interact with are two knobs, and it's unclear when you want to change just the temperature at constant flow at what ratio you need to adjust those two control knobs. So typically you take a guess at it, stick your finger under there to provide feedback, and then provide another control input and eventually get it close enough. So in that case, the two functional parameters of flow and temperature both map to both of the design parameters, hot knob and cold knob, as shown in the matrix below. It's a fully populated matrix. On the other hand, the faucet on the right is axiomatic. So there are still two controls, and there are still two functional requirements. But now I've separated the functions from the design parameters, and when I lift with angle 1, I adjust only the flow. And when I rotate about a vertical axis, changing angle 2, I adjust only the temperature. And it becomes very easy now to independently adjust either design parameter, either functional requirement. Many of you may be familiar with IDEO. It's a Palo Alto company, came out of some Stanford professors' work, well known for their innovation work, and in particular their ethnography work, their front-end understanding and having empathy for customers and being able to see opportunities before customers even know enough to ask for them. So they have a deck of cards out there that we like to use. You can get an iPhone version of it or an iPad version of it as well. But it's a 51 technique card deck that encourages people to go out and look or observe or build simple prototypes to try things, or gives instructive methods to learn more about their customers, etc. And so we normally like to ask our students to go through that deck and pick a couple that seem to resonate with what they're working on and what they might be interested in doing, and going out and trying it and seeing what they can learn about their customer. If we had more time, if this were not tape delayed here, we'd ask you guys in the board here how many ways you know to move a liquid. And after a few minutes, we probably have a good list of 10 or 15 things. Things like using gravity, things like changing its form and throwing it, things like a centrifugal pump or a positive displacement pump, etc. And eventually, if I gave you even a few more minutes, you'd have this entire list shown here, or not. And so the point here is that mankind has known how to move a liquid by these ways for quite some time now. In some cases, a very long time, in some cases more recent. But the point is, these are all known ways to move a liquid. But yet, when most of us were tasked with how we move a liquid, we'd think of only the few ways that we're familiar with. And we would perhaps not even consider magnetorestrictions or thermocapillary effect or electroosmosis, etc. And so this leads to the train of thought behind another technique that we teach, known as theory of inventive problem solving, or TREES. This comes out of Genrik Altschuler's work, former patent examiner in Russia. And he basically reasoned that if you try to take your problem and work directly to your solution, as shown by the dotted path above, that can be a very elusive, difficult path to find. What he says instead is that your problem has probably been solved by many other people, or at least a functionally similar version to what your problem is, has been solved many, many times by other people, perhaps in unrelated industries that you would never even consider looking at. And so he suggests taking your problem, genericizing it, then studying generic solutions. How have other people solved problems that are related to yours? And then how do you tailor everything you've seen in these other solutions to come up with a great innovative solution to your own problem? So that's kind of a simple explanation of a rather complicated technique to actually do that mapping, to genericize your problem, study the generic inventive principles, and come up with your solution. But that's an overview of a method that we use called TREES. Trimming is another one that involves functional understanding of your problem. product on the left, if you're as old as I am, you'd recognize as a tape recorder, named such because one of its principal functions is to record sound. And oh, by the way, it can then play it back so you can listen to what you recorded. So for many, many years, tape recorders recorded and played back sound. And you bought one in general based on price. There were many competitors making something that looked almost like the old Panasonic shown here, and you would buy it based on price. And along came Sony, sold tape recorders that can't record. They called them a Walkman, and they had an AM/FM radio in early versions, and later it changed tape to CDs and mini CDs, and eventually to memory sticks, etc. But the point is, they changed the game by questioning the function of the original product, namely the record function, which is the most expensive function to execute in the original product, and one of the bulkiest ones. Got rid of it and created a whole new industry. We teach 6 rules of trimming, kind of a variation of what comes out of some of the trees literature and some work done by Dave Verdoon, who works for C2C and does a lot of consulting work in the systematic innovation domain. So anyway, these 6 rules help a team or an engineer who's decomposed their problem functionally systematically examine these rules for trimming opportunities. Most engineers think more, bigger, faster, etc. And often there's a much easier way to very quickly come up with an innovation by removing something that nobody ever questioned or combining things in a way that nobody ever saw before. Lateral benchmarking is another one. It's fairly commonly used in practice, but most students never really give it much thought. But it's the idea that if you can identify a core aspect of your problem, whatever you're working on, where you're weak or you need some help, and you can identify who in the world is the best at that, you can go out and study that. So not just study cars and trucks, because we make cars and trucks are similar, but go study somebody who's functionally good at whatever it is you're trying to do. And the example shown here was where Southwest Airlines was trying to shave time off their turnaround time on the runways, and they went out and studied Formula One pit crews and shaved 20 minutes off the turnaround time for their multi-hundred-million-dollar airplanes. So saved an awful lot of money in idle time of the biggest resource of their company. Edward de Bono is well known for his work on creativity. In fact, you'll see one of his techniques in part 2 here with Kleinke shortly. But if you take this idea that we mentioned right up front about bisociation, taking some random stimulus and trying to use it to come up with a great idea, and you kind of really force that issue, now you come up with different ways to make what seem like really crazy statements. And then you take each of those crazy statements and you apply structured methods to try to move toward or generate movement towards new ideas. So one simple example might be, why don't I make rounded bottom hemispherical drinking glasses? So when I put them down, most people just think that's useless. I put them down and they'll fall over. But if you start to think about, for example, the benefits of that, well then maybe guests wouldn't accidentally or without giving it much thought, put drinking glasses that would sweat condensation onto your nice wood furniture because they would fall over. Or you'll drink more in the bar because you can't put your drink down, so you'll hold it all night. So you might be able to find the useful aspect of that, and then maybe you end up selling rounded bottom drinking glasses with coasters specially designed to receive them, and that's the only place somebody can put them down. So that we actually like to make a table that lists all 5 ways here of generating pose plus another way, a 6th way where you just come up with a crazy idea, and then look at all 5 ways of generating movement. So we end up with a 30-cell table and encourage people to come up with at least one idea for every cell of that table. And it's hard work. It gets you thinking really out of the box, so to speak. But when you're done, you end up with a lot of ideas that you never would have had by sitting around, buying donuts, and having a brainstorming session. Once you have all these ideas you came up with from many of these techniques we've just talked about, we like to organize them into what de Bono calls concept fans. essentially a mind map of the design space. As shown here, you list your problem objective on the right, cope with the water shortage. And then if you were just beginning with that, you might think of 3 broad ways you can do that: reduce consumption, increase supply, or do without. Then you take each of those and you drill a little bit more specifically ways you can reduce consumption. So for example, one of those would be discourage use. And then you think again, how are the ways I can discourage use? And so you build this fan or tree of the design space. And so what we like to do is, once we do have 100 or 200 ideas, map them into such a concept fan, look for branches that have very few ideas and try to generate more ideas. And oh, by the way, think of branches that are missing outright. Is there something else we could do fundamentally from a broad conceptual level that none of our 200 ideas are doing? And there might be some great white space in design there. So that wraps up part 1. We're going to break this video just for parsing sake and video size sake. And Daryl Kleinke will be with you with part 2 in just a second.